Hello, everyone. As I told you, I'm going to start a new session today dealing with exponents and logarithms. So maybe in this session, we'll discuss some exponents and look how we solve exponent functions. And then next time, we'll do the logarithm. Why we are talking about both of these? Because these are inverse functions. So um, a power, like an exponent function, and um, a logarithmic function are two inverse functions. Let me show you how they look. Let's pick something that everybody would be familiar with. So if I say, for example, so if I want to draw, say, uh, y equals e to the x, e to the x function, we know that every value or e raised to any number, this number will never yield a negative value. Meaning, if even if x is very small, now e to the x and x is negative 1 billion, then it's like 1 divided by e to the billion, which is almost infinity. So this function is asymptotic with the x-axis. But on the positive side, you can never get a negative y, no matter how you make x, unless x is imaginary. We know that if x is 0, y would be 1 for any base, anything raised to the other than 0. Any number raised to the power of 0 is 1. So this is 0 and 1. If x is 1, you get e, which is 2.71 something. If x is 2, you get e squared and so on and so forth, and your function would be pretty much almost going parallel to the x-axis, very close to it, not like I drew it, and then it starts getting higher and higher very quickly to go to infinity. Now, the opposite of that, or the reciprocal or the inverse function, is, let's say, y equals natural log of x. You cannot get a natural log of a negative value, okay? So the y here, I'm sorry, the x here cannot be negative. So really, the x is only positive, and the function is asymptotic with the y-axis. Natural log of 0 goes to negative infinity. I know that if x is 1, the negative or the natural log of 1 is 0. So this point, which is 1 and 0, is on the graph. If x is e, natural log of e is 1. So you get e and 1. And do you see what happens for inverse functions when you draw them? Of course, they are not drawn to scale. But if they were drawn to scale, this line that passes through the origin and has a slope of 1 would be a mirror image. It would make mirror image of the functions. And that's always going to happen for inverse functions when they exist. Okay? We do, remember we talked about the square root function and the square function. But the square function, of course, has two branches, but for the square root, it's only one branch. If you draw a line with slope of 1 at the origin, it would be an axis of symmetry for the square and the square root, and so on and so forth. So that's something nice to know, is that if you have and that's why we are going to work for both of these. So what is the power function? Something raised, the easiest thing, of course, to think about is the tan, because You know how to square the 10 is 100, cube 10 is 1,000, take it to the power of 4 is 10,000, and so on and so forth. But what does it mean? When I say x cubed, for example, I mean x is multiplied by itself 3 times. And it's especially when deal with scientific notation, and you have, for example, you want to find the number of, like I think Sir Isaac Newton tried to do, the number of hydrogen atoms, that can fill the universe, or how many are these? Of course, I'm not going to write them, so you can take an abbreviation and say times 10 to the power of something, meaning instead of writing 100 zeros, I write 10 to the power of 100, which is a Google, as you know, right? So we have some rules, and you will see very similar rules for the logarithm next time. Rules of exponents. So if I have x to the power of a multiplied by x to the power of b, this can be simplified as x to the power of a plus b. So the multiplication, notice x and x, it has to be the same base. If it's x to the a times y to the b, I cannot do anything to that. I cannot simplify it. But if it's the same base, 3 squared times 3 cubed, 4 or -4 squared times -4 cubed, and so on and so forth, I can add the exponents. So the multiplication became an addition of exponents. So can someone tell me what would happen if I use division instead of multiplication? You got it. I know you got it. Because the inverse of multiplication is division, and the inverse of addition is subtraction. So that's an easy way to remember that. A minus b. This is the inverse of that, so this is the inverse of that. So exponentiation simplifies multiplication into addition. It simplifies division into subtraction. So how does it simplify exponent? So x to the a quantity raised to the power of b. Any idea? It becomes x to the a times b. So the exponent in the power becomes a multiplication here. So it simplifies the exponentiation into multiplication. So how would it simplify the roots? Yeah, the opposite of that. So if I take the bth root of x to the a, it becomes x to the a over b. Exponent inverse is root. Multiplication inverse is division. We also say that x to the negative a equals 1 over x to the a. What does that mean? It means instead of writing 1/2, I can write it 2 to the -1. -1 here, we call it the reciprocal, if you remember. So if I tell you what is the reciprocal of 2, it means make the numerator denominator and the denominator numerator. So if I have a negative exponent, I can move it from numerator to denominator by changing its side, and vice versa. Meaning if I say 1 over x to the negative a equals x to the a. Now, if I multiply both sides by x to the negative a, we get a very famous rule, right? If you multiply both sides by x to the negative a, x to the negative a divided by x to the negative a is 1. They cancel each other, so you end up with a 1 on the left-hand side. But what is that? Go back to the first law. It tells you that if you have two bases with different exponents multiplied, you add them up. So you get x to the a minus a, which is x to the 0. And that is telling you why any number raised to the power of 0 except 0 will yield 1. Okay? And these are the most common laws that we can use to simplify exponents or to solve exponential equations. Let's take a few examples on those. So let's say I have the first example. I'm going to say, let's say any number, let's 5 to the power of 2x equals 5 to the power of 1 minus x. Well, it's the same base, so the exponents must be equal. We will prove that next time when we do logarithms, okay? But for now, I say, well, if the bases are the same and the left-hand side equal the right-hand side, so definitely 2x must equal 1 minus x. I'm going to add x to both sides and get 3x equals 1. I'm going to divide both sides by 3, and I get x equals 1/3. Okay, so this one is very easy, right? Okay, let's take another example. Let's say can we do, for example, let's take something, let's take something similar to that. Equals 25. You say, oh, the left-hand side has an exponent, the right-hand side doesn't. The base here is 5. Can I make the base here to be 5? What is 25 in terms of 5? It's 5 times 5, right? Or it's 5 squared. So now, if I say the same base as before, then 1 minus x would equal 2. Which means if I subtract 1 from both sides, I get negative x equals 1. Divide both sides by negative 1. I get x equals negative 1. And that's also simple. So now if I have to learn how to square or cube numbers so that if the base is not the same, and usually if they give you a problem like that, you know that one of the bases can be written as a power of the other base. Let's say we didn't do the logarithm, so let me pick a problem that I think these are pretty straightforward, right? If we say so, let's take 3 to the 6x minus 2 equals 27 to the x plus 1, whatever. Okay, so now I can see that, again, since I have a 27, you have to think in terms of 3, right? So you say, well, 3 times 3 is 9, times 3 is 27. So 3 times 3 times 3 is 27. So I can write the 27 as 3 cubed. And then this 27 is raised to the power of x plus 1. What rule was that? X to the a, everything to the b is x to the a times b. So I can now simplify the right-hand side and say it's 3 raised to the power of 3 times x plus 1, or it's 3 raised to the power of 3x plus 3. And now I reduced it to the previous ones. And now I can say 6x minus 2 equals 3x plus 3. I'm going to subtract 3x from both sides and then add 2 to both sides. So that will give me 3x equals 5. Divide by 3 both sides, and I get x equals 5/3. So I think this would be the same thing. Notice that I could have solved that slightly differently. I could have written, so on this side, I could have left the 27 raised to the power of x plus 1 as it is and say that 3 is the cube root of 27 raised to the power. I want to make it looks hard, but show you that it's the same thing. It's not hard at all. Did you see how I can write this? The bth root of x to the a, or just x, is x to the a over b. So this can be written as 27 raised to the power of 6x minus 2 divided by 3. And that equals 27 raised to the power of x plus 1. That's how we write the cube root. We divide the exponent by 3. If there is no exponent, I write 1/3. Yeah, cube root of 27 is 27 raised to the power of 1/3. And now because the base becomes the same, I have to say 6x minus 2 over 3 equals x plus 1. I'm going to multiply both sides by 3. And the rest is history, because I will get 6x minus 2 equals 3 times x plus 1, or 3x plus 3. So I will end up with the same equation, same answer. Finally, one important thing I have to mention here is that if you get x to the a raised to the power of b, that's completely different from x to the a to the b. What does that mean? This means that you take x to the a and then raise the sum to the power of b. So for example, if I say 2 cubed 4, it means 2 cubed is 8 to the power of 4, which is 64 times 64, right? Which is 4,096. But 2 to the 3 to the 4, it means you have to perform the outside. We usually go from top down. So you say 3 to, if there is a 2 here, I would say 4 square is 16 and 3 to the 16. So 3 to the 4 is 81. And this number is humongous. This number, you know that 2 to the 10 is slightly more than 1,000, right? 1,024. So let's say it's 1,000. So when you take 2 to the, I'm sorry, I said 2 to the 10th is 1,000. So 2 to the 80th would be 1,000 to the 8th power, 1 with 24 zeros next to it. 4,096 is nothing compared to that number. Okay, so when you write it, you have to be careful to use parentheses, or else it would be completely out of proportion. It would be very wrong. Okay, So that was just a side note for you to realize this problem. Next session we'll do logarithmic, because suppose that was a 3 and that was a 25 instead of 27. There was no way we could solve it. Why? Because what is there is no, I cannot reduce the 27, the 25 into 3 or raise the 3 to a power to become 27. So in that case, I cannot solve these exponential or exponent equations. I had to revert or to resort to logarithms, which will be introduced next time. Okay, hope this was helpful, and see you next time. Thanks.